Hello, my name is Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is Module 9 in my Computer Networks lecture series, where I talk about the retransmission of frames. And so, I guess, at this point, we've completed the discussion of error detection. So by now you know very well the different methods for detecting errors, or some of them anyways, in a frame. And in particular, we finished off that discussion with an example showing that the cyclical redundancy check is quite good at detecting frame errors. And so going forward, we're going to kind of assume that, if a frame is bad, we know about it. And the next step in our discussion, therefore, is what to do. So we've received a frame, we run our CRC, check on it, and it says, sorry, there's an error somewhere in this frame. And of course, we don't know how many errors there are, and we don't know where those errors might be. And so the choice, I guess the first choice we have to make is whether or not we want to even keep the frame. So there are some types of traffic, in particular voice, audio traffic, streaming audio, perhaps some streaming video, that can tolerate some errors. So I suppose one option is for us to keep the frame, pass it up the protocol stack, and hope that the application is able to make some sense of it. But in reality, the default for most protocols is to just throw the frame away, basically. And so given that, if we decide to discard a packet, what we're going to talk about is essentially the mechanism that governs the retransmission of that packet, because we can't do without the data. So we can't be downloading an app and have just chunks of it missing. So when a frame is received and the CRC tells us it's bad, we need a mechanism for the frame to get resent. And the techniques, I suppose there's a few different ways to refer to these techniques, but the primary term that we use is ARQ, which is short for automatic repeat request. And these are the algorithms that manage packet retransmission. And the interesting thing about an ARQ algorithm is that it actually gives the illusion of an error-free link. Assuming that our error detection scheme is good, and we've seen that CRCs are very, very good, we can spot every single frame, practically speaking, that's bad. And if we just sort of get those frames to be retransmitted and we refuse to accept the frames until the CRC checks out, then as far as the upper layers of the protocol stack are concerned, it seems like our error-prone physical layer with our probability of bit error is in fact error-free. And so the higher layers of the protocol stack will essentially assume that the packets that we're working with are free from errors. But of course, as with all things, the benefit of having the illusion of having an error-free frame comes with the drawback of basically reduced throughput. So if we have if we're spending time retransmitting old frames, obviously that's using up throughput or bandwidth that could be used for the transmission of new data packets. And so one of the things that we're going to be talking about in the upcoming modules is to sort of quantify the effective throughput penalty that we experience when we have to retransmit, bad frames more than once. And we're going to be able to quantify exactly what the effective throughput is. So the other thing, or the next thing I want to mention is that, at this point in our lecture series, we are still at the logical link control layer. So basically just the protocol stack that's sitting right on top of the physical layer. We know the physical layer is prone to errors, and so it makes sense that we would be checking for those errors, and we would be retransmitting over that physical layer if any of our received frames are bad. So ARQ makes sense to plug in at the logical link control layer. However, later on we're going to see that we actually see ARQ again much higher up the protocol stack in the transport layer. And it seems strange that, we should have ARQ down at, the logical link control layer and then add it again higher up because, haven't we already fixed the problem of errors? And it turns out that there are actually many, I don't know about many, but multiple sources of packet loss and packet error. And so one of the sources is the noise and interference that we experience at the physical layer. And we do indeed clean that up with ARQ at the logical link control layer, or at least the data link layer, layer 2. However, it turns out that in a multi-hop mesh style network like the internet, another way to lose packets is to have too many packets sort of crowding into a router all at one time and having the buffers or the capacity of that router be overwhelmed, and the result of that is actually dropping packets higher up in the protocol stack. And we're going to be talking about that in more detail once we get to that level of the protocol stack. But just be aware, ARQ, even though we're seeing it for the first time at the data link layer, at layer 2, we're going to see it again further up in the protocol stack. And the final point that I want to make is that not all data link layers, not all logical link control sublayers actually use ARQ. So for many systems, in particular wired systems, so for example Ethernet or fiber optic systems, the physical layer is actually quite clean. So we don't really have a lot of errors. Plus, wired systems tend to want to go really, really, really fast. And so often the design decision is made not to implement ARQ in a wired system because errors aren't that common and the overhead of implementing ARQ would reduce the really high throughputs that we're trying to achieve. So in general, ARQ at the data link layer, at layer 2, tends to be most common in wireless systems. And that's some of the examples that we'll be pulling on as we work through some of these concepts. As we're going to learn, there are a number of different kinds of ARQ algorithm. There's a bunch of different ways we can manage the retransmission of bad frames. However, they can all kind of be presented in sort of a unified fashion, in kind of a generalized framework. And so most ARQ algorithms are variations of what we're going to refer to as the sliding window protocol. And I'll present the sliding window protocol in the coming slides in a very general way, and then we'll talk about different ARQ algorithms as particular versions or subtypes of the sliding window protocol. And in the sliding window protocol, we essentially have two types of frames. The first one is the information frame, or I-frame. And the information frame is, just as the name suggests, the frame that carries the actual user information. So it's a frame with a payload of user information and with some headers and with a header and a CRC. The second type of frame is an acknowledgement frame, or ACK frame. And the ACK frame is basically a frame that we send to acknowledge the reception of one or more information frames. Now, sometimes an ACK frame can be a special dedicated control frame. So we could send an information frame, for example, to a node, and then the node would just send a short little control frame back saying, yeah, I received the frame. Other times, in other types of protocols, ACK information is actually piggybacked onto an information frame going in the opposite direction. And this is good for sort of protocols where, the bidirectional communication is approximately balanced. So we send an information frame to one node. That node needs to send an information frame back anyways, and so it buries the ACK information into the header of the return, or the information frame that is going back along the return path. But And in the coming slides, we're going to, dive into a fair bit of detail. We're going to have a bunch of parameters that we're going to be talking about. But as we get into this level of detail, the most important thing for you to remember is just the basic mechanism that we're talking about. So all the sliding window protocol is about is the basic mechanism where we send an iframe, and if it's received, we send an acknowledgement or an ACK back saying that it's been received successfully. So we send the iframe, and the ACK indicates a successful reception. And that's really at the core of what we're going to be talking about in the coming slides. So if we're calling this protocol the sliding window protocol, I guess a logical question is, what about the window part? I mean, why do we call it sliding window? And as you would imagine, information frames have sequence numbers that are monotonically increasing. They're always going up. And these sequence numbers can be used by the receiver to spot missing frames and also to put information frames back into the right order. And so how could packets possibly arrive in the wrong order? Well, remember, ARQ is not only used just on a direct physical layer link between two nodes, it can be used over a multi-hop mesh network where there happens to be different paths that packets can take between the transmitting node and the receiving node, and sometimes one path is a little faster than the others. And so in theory, we could send 4 packets out onto a mesh network, and rather than having them arrive 1, 2, 3, 4, they could arrive 1, 4, 2, 3, depending on the paths that those packets take. So sequence numbers are useful for spotting missing packets and putting packets back into the right order. And the sequence numbers that we use, so we're going to use the number n the variable n to represent the sequence number. And the question is, well, how do we determine the value of these sequence numbers? Well, there's a couple of ways. The logical way to do it, and many protocols adopt this approach, is to just use the frame number as the sequence number. So the first frame we send will be frame 0. The second one we send will be frame 1. The third one will be frame 2, and so on. However, some protocols do deviate from this. So in some cases, the sequence number is actually the byte index of the data that we're carrying in the payload. So for example, let's consider a system that sends its first frame, and the first frame contains 4 bytes. So the sequence number for that first frame would be 0, because the index of the first byte in its payload is 0. But then when it sends the second frame, the sequence number for that frame would be 4, because it's the 4th byte in the information stream. Regardless, it's important to remember that sequence numbers ultimately are binary integers that will eventually wrap around. And I mean, yes, we can we can sort of allocate a lot of bits to our sequence number and make our numbers very, very big. But we can't use floating or fixed point representation. We have to use integers, and to avoid ambiguity. And eventually those integer numbers will wrap around. And especially considering the vast amounts of information that we send over the internet, even sequence numbers that can go up into the billions will eventually wrap around in a relatively short amount of time. And to address this, and to overcome the potential ambiguity that we might experience with more than one frame having the same sequence number due to wraparound, we need to limit how many frames can be outstanding before an ACK must be sent. And this is achieved using Windows. So Windows set a maximum on how many frames can be sent or received before an ACK must be transmitted. And the idea is to keep the windows short enough that we don't risk wrapping our sequence numbers all the way around before an acknowledgement is transmitted. And so to put a little bit more detail behind this, I'm going to do an example to show you what I mean. So to give you an example of what windowing is all about, I'm going to introduce a diagram that we're actually going to be using quite a lot in this lecture series. This is, what you see on this slide is essentially a timeline diagram. So you can think of these arrows as representing the, time. So as we move from left to right along these arrows, we're increasing in time. And each arrow is labeled with a different node name. So in this case, node 1 we can think of as the transmitting node, and node 2 as the receiving node. And we've got two diagrams, and the top part of the slide is going to consider the case where we're using no windowing. Okay? And so basically, I'm going to use these timelines to represent the flow of packets between a transmitting node and a receiving node. And I'm going to represent the flow of a packet as an arrow. Oh, let me see if I can make a straight line here. And so you'll note that the arrow starts at the transmitter, ends at the receiver, and there's a certain amount of time that it takes. So we transmit at this point in time, and then we receive, at this point in time. And that represents, perhaps the propagation delay through the channel, plus the fact that every link has a certain finite throughput. So this just means it takes us a certain amount of time to clock the bits through the channel, if you like. So, just to remove some of these. So in the no windowing case, because this frame is flowing from the transmitter to the receiver, this is an information frame. And we are using sequence numbers in this example. And let's say that we're using a 2-bit sequence number. So the numbers can go from 0 to 3, and then they wrap around right back to 0. And for some ARQ protocols, we get an acknowledgement immediately back every time we send an information frame. However, not always. Sometimes the receiver will wait for a group of frames to gather up before sending an acknowledgement. And this is often done to sort of reduce the amount of overhead or extra bits that are sent through the channel. And so in this case, let's consider an example where we actually send 4 frames through the channel. Actually, let's do 5 frames through the channel. And each of these frames will be given a sequence number, or each of these frames will carry a sequence number in its header. This first frame would be sequence number 0. The next one would have sequence number 1, 2, 3, and then because we've only got 2 bits for our sequence number, we wrap around to 0 again. And so let's say after receiving 5 frames, the receiver decides to send an acknowledgement. Now, in all cases that I'm aware of anyways, the acknowledgement will contain the sequence number of the frame that we're acknowledging reception of. And in the case where we receive a whole bunch of frames in a row, because we only send one sequence number back in our acknowledgement, usually we acknowledge the most recently received frame. And the transmitter knows, okay, well, if you've received up to that point, then you must have received all of the frames before that. And so for reasons that just kind of have a lot to do with convention, actually, the acknowledgement is often, or the acknowledgement often contains the sequence number of the frame that we're expecting next. So we've received frame 0, and so the receiver is going to send its acknowledgement back saying that it's now expecting frame number 1. Now you'll notice here that there's ambiguity. So we have sent 2 frames that have a sequence number of 0. And so an acknowledgement with a value of 1 is appropriate after having received this frame, but it's also appropriate after having received that frame. And so we're not really sure which frame is being acknowledged here. And so, in this particular case, we could say, well, let's just kind of assume, let's just hope for the best, and let's just assume that, this second frame was the one that we received. And that's fine in this particular case, but it can run into problems when we have frames that do not successfully arrive at the receiver. And so for that part of the example, oops, that's not what I wanted to do. There we go. So let's say we start transmitting again, and we transmit frame. So we've just finished transmitting sequence number 0, and so we've had an acknowledgement go back saying the receiver is now expecting the frame with sequence number 1, so that's what we transmit. And then we proceed and transmit another frame, but in this case, the frame doesn't arrive. And I represent that using this kind of broken arrow, this sort of, that doesn't quite arrive all the way at the receiver. And so this transmitted frame would also have a sequence number. In this case, it would be sequence number 2. And the fact that it's broken indicates that it doesn't arrive. Does this mean that it actually doesn't arrive, like it's lost somewhere? Well, sometimes, like in a wireless link, if we are very far away from the receiver and we transmit a signal, that signal can be so weak as to be completely obscured by the noise, just the natural thermal noise in the channel. And sometimes we say that that the signal is below the noise floor when this happens. And so we can kind of imagine an incredibly weak signal being swamped out by noise as just being undetectable. So in that sense, it didn't arrive. However, most often the frame does actually arrive, and we get enough of a frame that we know that we've received a frame, but we do our checksum on it, and the checksum indicates that some bits are in error. And so then we have to discard the frame. And so this broken arrow represents both frames that are so weak that we didn't even detect them, and frames that were strong enough that we did detect them, but they failed their checksum. And so let's say this frame is, the frame with sequence number 2 fails to be detected, and then all of a sudden we have a bit of a string of bad luck where we have another frame that's not, another frame, and another frame. And so we've had 4 frames in a row that didn't arrive. Let's say we had a big long burst of interference perhaps, and all 4 frames in a row were corrupted. And so in this case, this would have sequence number 3, then we would wrap around to 0, then we would wrap around to 1. And then at this point, the receiver decides to send its acknowledgement back. And because the last frame that was successfully received had sequence number 1, the acknowledgement is going to say, okay, I'm expecting sequence number 2 now. And we did send 2 and 3 and 0 and 1. And so now there's some confusion at the transmitter regarding whether or not we were referring to this first frame or this last one that didn't arrive. And so you can see this is kind of trouble, right? So this business of wrapping around the sequence number can cause a lot of problems. And of course, you could sort of look at this example and say, well, let's not just choose 2 bits, let's choose a really, really big number, and then it's very unlikely that we'll wrap around. And, there's 2 reasons why we want to avoid that. One is, eventually we will wrap around due to the huge number of frames that we send through most high-speed digital links today. And so we want to be absolutely sure. Plus, the more bits we allocate to our sequence numbers, the more room we take up in our header and the more overhead bits we place into our protocol. And that reduces the amount of the channel that we have available to send actual user data. So now let's consider a case where we have a 2-frame window. So, 2-frame window. So that means we can only have 2 frames outstanding before an acknowledgement needs to be sent back to the receiver. And so again, node 1 is the transmitter, node 2 is the receiver. And so let's start out with copy. So that means we can send only 2 frames, the first one having a frame or sequence number of 0, the second one having a sequence number of 1, and then we have to send an acknowledgement in reply. So by convention, the sequence number that we contain in our acknowledgement frame is the sequence number of the frame that the receiver is expecting next. And so in that case, we would say we want frame number 2. And once the transmitter receives the acknowledgement, it's then clear to send 2 more frames. And so if it does that, let's consider a case now where the first frame arrives okay, but the second frame, if I can manage to select it here, arrives in error. Let's go back up too, so we're a little bit neater. There we go. So this frame would have sequence number 2, the next one would have sequence number 3. And so we've received the first one, didn't receive the second one, and so when we send our acknowledgement, again, the acknowledgement always has the sequence number of the frame that we're expecting next. So we've received 2, we haven't received 3, and so from the receiver, as far as the receiver is concerned, it's still waiting for frame 3, and so it's going to have sequence number 3 in its acknowledgement frame. The transmitter gets this and it says, oh, I just sent frame number 3, but the receiver is still expecting that frame, so that means it must not have been received correctly. And so what the transmitter will do is then just retransmit frame 3. So we transmit frame 3, and there's no reason why we can't send another frame, because we're allowed to send 2 frames before an acknowledgement comes or has to be returned. So we'll send the next frame, so that is the one where our sequence number wraps around to 0. And then when our acknowledgement gets sent back, again, it will contain the sequence number of the frame that we're expecting. I always seem to pick up that 2. The acknowledgement contains the sequence number of the frame that we're expecting next. we've successfully received frame sequence number 0, and so the next sequence number we're expecting is sequence number 1. And so hopefully with this bottom example, you can kind of see how windowing works. We basically sort of don't have more than 2 frames outstanding. And because of that restriction, we can't wrap our sequence number around, right? So obviously in this top example, we wrapped our sequence number around because we transmitted 5 frames at a time, which was enough to wrap around our 2-bit sequence number. As long as the window is shorter than the maximum value of our sequence number, we don't experience this problem. And so basically all ARQ algorithms will have some kind of windowing incorporated into them. So in order for a sliding window protocol to work properly, there's certain information that needs to be stored at the transmitting node and certain information that needs to be stored at the receiving node. And let's start with the transmitter first. The first parameter I want to talk about is NTX, and that's basically the sequence number of the frame that we're going to send next. So if we send frame 0, then NTX is going to be equal to 1, because 1 is the sequence number of the very next frame that we're going to send. The next thing the transmitter needs to do is keep track of the frames that have been acknowledged by the receiver. And so NA is basically the highest acknowledged sequence number that has been received by the transmitter. So the transmitter is going to be watching these ACK packets, and every time a new one arrives, whatever sequence number is contained in that ACK packet is recorded in NA. The next parameter is basically the transmit window size, WTX. And WTX is the maximum number of unacknowledged frames that the transmitter is allowed to send. And so in the example on the previous slide, the transmitter sent 2 frames before waiting for an acknowledgement. And so in that case, WTX would be equal to 2. And said another way, the frame of the sequence number of the frame that we're going to send next always has to be less than or equal to our most recent acknowledged sequence number plus whatever our window size is. And so let's consider an example where NA is equal to 4. So that means the most recent number that the transmitter has seen in an ACK packet is 4. And remember, the ACK packet contains the sequence number of the frame that the receiver is expecting next. So sequence number 4 hasn't been transmitted yet. This is the one that the receiver is expecting. Let's also say, for the purposes of this example, that WTX is equal to 2. So that basically means that the transmitter can send, I guess, okay, to send sequence number 4 and 5, and then it has to stop. So we can only send 2 outstanding frames before we have to wait for another acknowledgement. And so after sending frame number 4, the value of NTX is going to be equal to 5, right? So we've sent 4, and that means we're going to send 5 next. After we send 5, NTX is going to be 6, because remember, NTX stores the sequence number of the frame that we're sending next. And so this equation holds water. So NTX has always got to be less than or equal to our most recent acknowledgement plus our window size. And in this case, if our most recent acknowledgement is 4 and our window size is 2, NTX has to always be less than or equal to 6. Okay, so the receiver is a little bit more complicated because the receiver, in some cases, in some realizations of the sliding window protocol, will actually buffer out of order packets. So again, sometimes packets can arrive in the wrong order. So if we transmit packets 0, 1, 2, 3. Maybe packet number 1 arrives before packet number 0. And so we have periods of time where we have one packet, but there's basically a hole in our received packet sequence. This can also happen when, let's say, we send packet 0, 1, 2, and 3, and 0 arrives correctly, 1 arrives correctly, 2 fails its CRC, but then 3 arrives correctly. So again, we have a little bit of a hole. Some protocols don't allow this, but others will buffer and wait for those holes to be filled in from retransmissions. And because of that, we've got a few more variables to keep track of in the receiver. And so I'm just going to sort of go through the variables. I'm going to describe them on this slide as best I can, but then we're going to very quickly go into an example that will hopefully solidify how all of these variables kind of work together. And we're going to keep on going through example after example in the upcoming modules, and hopefully by the end of all these examples you'll see and be comfortable with what all these variables mean. So in the receiver, the first thing that we keep track of is a variable called NRX. And basically all packets below NRX have been received, and I will add in order. So if NRX is equal to 3, that means that we've received packets 0, 1, and 2. And 3 is sort of the next one that we're expecting. The value, or the number that we send in our ACK frames, NA, will always be less than or equal to NRX. In most cases, NRX is the value that we send in our ACK frame. So again, if you'll remember from our earlier examples, the ACK usually contains the number of the frame that we're expecting next. That's what NRX stores. And so if we've received frames 0, 1, and 2, NRX will store frame 3. And so the number 3 is usually, or would be what we would send in our ACK packet back to the transmitter. As I said, some receivers will buffer out of order packets. And so we might have a case where we've received packets 0, 1, and 2, but we were missing 3, and then we received packet number 4, for example. And so we still need to record the maximum sequence number of the packet that we've received, even if there happens to be some holes in that packet sequence. And that's what we use the variable ns for. And ns is one more than the maximum received sequence number. So let me just give you a quick example, and let's assume that we're using a sequence number that is more than 2 bits. So we have, we've received frame 0 correctly, 1, 2, 3 was not received. Then we received 4, 5, 6 wasn't received, and then we received frame 7. So in Rx always is one more than the maximum sequence number of the frames that we've received correctly in order. So we've received 0, 1, and 2 correctly before we encounter our first hole. So NRX will be equal to 3. NS is one more than the maximum sequence number we've received, regardless of whether or not there are holes in the packet sequence. And so in this case, NS would be equal to 8. And so that's the difference. And so if there's a difference between NRX and NS, that means we've got a sort of a chunk of data here where we might potentially have some holes. So in other words, NRX is always less than or equal to NS. WRX is what we call the receive buffer, the receiver window, the receive window. And it's basically how many new packets the receiver is willing to buffer before an acknowledgement is sent. And let's say if X is a new packet sequence number, it's only accepted if it falls between the sequence number that we're of the most recent in order, or the sequence number of the packet that follows our most recent sort of in order successfully received sequence of packets, and NRX plus the window size. ACKs always contain the current value of NRX. We never ever send NS. And the window size of the receiver is usually less than or equal to, my formatting wasn't right there, the window size of the transmitter. Because there's no point having a buffer, a buffer reserved for 10 new packets if the transmitter is only ever going to send us 2 new packets at a time. And so this was kind of a lot of parameters and a lot of fairly general discussion. What I want to do next is show an example of a packet exchange where we kind of represent all of these variables on the example, and you can see how they update as packets are sent and received and acknowledged. So the main purpose of this example is to kind of demonstrate how the sliding window protocol is supposed to work. But another kind of side benefit of this example is that it's a good illustration of kind of the way that you need to think when trying to understand communication protocols. It definitely is good to be able to step back from something and have a high level view or picture of how things are supposed to work. But a lot of protocols, when you try to take them in all at once, seem fairly complicated. However, protocols, pretty well by definition, are basically just a series of steps that 2 nodes need to follow when communicating. And so often the best way to understand, the real details of how a protocol works is to dive in and just very methodically go kind of step by step. And that's the way that we're going to approach this example. So in this particular example, we've got, I call it a 4-bit example because it's a 4-bit sequence number. So we're going to wrap around, our sequence number is going to go 0, 1, 2, 3, and then wrap around to 0. The transmit window size is going to be 3. The receive window size is going to be 2 frames. And in our transmitting node, which is node 1, we've got 2 variables to keep track of. NTX, which is the sequence number of the frame that we want to send next, and NA, which is the maximum acknowledged sequence number that we've received in an ACK packet. In node 2, in the receiver, we've got, again, 2 variables we want to keep track of. NRX, which is 1 greater than the sequence number of all the frames that we've received successfully. And NS is 1 greater than the maximum sequence number that we've received, regardless of whether or not there are holes in that received sequence order. So we're going to start out by sending our first information frame from node 1 to node 2. And it's going to have sequence number 0. And so at this point in our timeline, the value of NTX is going to be equal to 1 because we've sent frame 0 and the next frame that we have to send is frame 1. Down here in the receiver, the value of NRX is going to also be equal to 1 because we've successfully received frame 0. There's no holes in our sort of received sequence. And NS, which is 1 greater than the maximum sequence number that we've received, in this case is also going to be equal to 1. So again, when we've successfully received a bunch of frames in a row and everything's in order and there's no problems, NRX and NS are always going to be equal to the same value. Now, let's send an acknowledgement. Okay, so the acknowledgement, the sequence number in the acknowledgement is always equal to nrx. So the acknowledgement will carry sequence number 1, which is the frame that the receiver is expecting next. And then at this point, basically the transmitter and the receiver are in sequence. So the next frame that the transmitter is going to send is sequence number 1. The most recently received acknowledgement value is also 1. And down here, NRX and NX and NS have not changed because no new frames have been received. So right now, everybody, the transmitter is ready to send sequence number 1. That's what the receiver is expecting, and that's what's been acknowledged. And so now let's send that frame, but let's include the situation now where the frame is lost. And so this is the frame carrying sequence number 1. Now, whenever the transmitter sends a frame, it starts a timer. And if it doesn't receive the frame by the end of the timer, that triggers a retransmission on the part of the transmitter. And so I'm not always going to mark in the timer sort of expiry, but in this case, we assume that we've got a certain amount of time, T, I don't know, let's call it expiry, I guess. And at the end of that time, if no acknowledgement is received for that particular frame, it is retransmitted by the node 1. And that retransmission occurs exactly where the timer expires. It's going to be an exact duplicate of the frame that was sent, so it's going to have the same sequence number. And then at this point, NRX increases to 2 because we've successfully received frames 0 and 1, and so now the next one we're expecting is 2. The maximum, 1 plus the maximum sequence number of all the frames we've received, in order or not, is also 1, so NS is equal to 2. The transmitter is ready to send frame number 2, so NTX is 2, but NA is still 1, because we have not yet received the acknowledgement for the frame that we just sent. So let's do that now. We send an acknowledgement. Acknowledgement contains the value of NRX, so the frame that we want next. And then at this particular point, the transmitter is ready to send frame 2. We've received an acknowledgement saying the receiver is expecting frame 2. NRX and NS are equal to 2 as well. And then once again, the transmitter and the receiver is in sync. And so now what we're going to do is I'm going to, just to sort of show you how this kind of windowing works, we're now going to do a sequence where the transmitter is going to send 3 frames in a row without acknowledgement, because its window size allows it to send up to 3 outstanding frames before receiving an ACK. And the middle frame is going to be received in error. And we'll see how this causes a difference now between the values of NRX and NS. Okay, as promised, we have now 3 transmitted frames. The first and the last one are received successfully, and the second one maybe gets received but has a bad CRC and so is thrown away. So the frame that the receiver is expecting and the frame that the transmitter is ready to send is sequence number 2. So this frame has sequence number 2. This frame has sequence number 3. And then we wrap around, and so the final frame has sequence number 0. And so at this point, we've just sent sequence number 0, so the transmitter is now ready to send sequence number 1. The last acknowledgement we received was for sequence number 2, so that hasn't changed. And we've seen some interesting things happen now on the receiver end. So NRX will not progress past a hole. So NRX is 1 plus the maximum sequence number of all the frames that have been received successfully and in order, and that's key. So we've received frame 2. Frame 2 is in order, but then we're missing frame 3. And so basically NRX is going to stall out right here. And so the value for NRX is going to be equal to 2 plus 1, or 3. Now NS doesn't mind there being holes in the order of received frames. It's always 1 plus the maximum. And in this case, our most recent frame is 0. So NS is equal to 1, right? So NS is 1 plus the last frame that we've received. And once we see a difference between NRX and NS, we know now that there's holes in the order of the frames that we've received. Okay, so now it's time for us to send our acknowledgement back. But before we do that, I want to say a few words about the receiver's packet buffer. So we know that we can buffer up to 2 outstanding packets. And there are a couple of different ways to define how we fill up this buffer. Some protocols could say, well, the number of packets in our buffer are basically the number of packets received since we last transmitted an acknowledgement. But for the purposes of this discussion, I'm going to assume that the received buffer is only filled up by out-of-order packets. So, for example, we received packet 1, then we acknowledged it, and then in our most recent sequence of 3 packets in a row, we received packet 2 first, and that was in order with packet 1. And so I'm going to assume that that packet 2 does not take a place in our received packet buffer limit, just because it's still in order. However, then we lose packet 3, and then we receive packet 0. And so packet 0 definitely would take up a place in our received window. And so at this point, we would say that we've got 1 sort of outstanding packet in our received buffer. Like I said, you can define it different ways, but this is the way I'm going to define it for the purposes of this example. So now we need to send our acknowledgement back to the transmitter. And this requires a little bit of thought because we've received some packets and we're missing others. So remember that the acknowledgement always carries the current value of NRX. And so this acknowledgement is going to carry the number 3. So now the question is, there we go. So now the question is, what, when our transmitter sends a frame, which one is it going to be? Well, from the transmitter's perspective, we've sent frames 2, 3, and 0. And we've received an acknowledgement for 3. Now remember, an acknowledgement basically is always the sequence number that's 1 greater than the frame that we've most recently, received in order. And so when the transmitter receives the number 3, it knows for sure that frame 2 has arrived successfully. But it doesn't know about frame 3, and it also doesn't know about frame 0. So there's a question in the transmitter's mind about which one, if either of these frames have arrived. It knows for sure that frame 3 hasn't made it, but it doesn't know whether frame 0 has made it or not. And so normally what happens is the transmitter will start a timer for every single frame that it sends. And the timer for frame 3 would expire before the timer for frame 0. And so it would send frame 3 just because that's the oldest kind of outstanding frame that it receives. Now if I just do a little bit of a point in time count here, the next frame that the transmitter wants to send is frame 0, or sorry, NTX is still equal to 1. The most recent acknowledgement it's received is 3. And at this point, we've had some interesting things happen at the receiver. So we've now had frame 3 arrive, which fills in our hole. And so NRX is now going to jump up to be 1 plus the most recent in order frame that it's received. And so it's now received frame 2. It's now received frame 3 thanks to the retransmission. It's now, and it had buffered frame 0 from before. And so frame 0 is the most recent in order frame that it's received. So NRX is actually going to be equal to 1. NS is also going to be equal to 1. And now these two values are the same, so we can now see that we're back in order, right? So as soon as NS and NRX are the same, that means that there's no holes in our received packet sequence. And so now finally, to conclude the example, the receiver sends one more acknowledgement back to the transmitter. It contains the current value of NRX, which is 1. Whoops. Which is 1. And so at this point, the transmitter is ready to send frame number 1. The receiver is expecting it. And that's the number that's been acknowledged. And so the transmitter and receiver are in sync again. So there was a lot going on in this example. The diagram got pretty messy here after a while. But again, just, and when you look at your page right now, it looks like kind of a mess, right? But again, remember that the way that we worked through this was just sort of step by step by step. At every point, the thing that happened followed a very sort of established logical rule. And I would encourage you to maybe take a blank sheet of paper and redo this example, sort of just construct it again step by step and make sure that you understand each step along the process. If you have questions, write them down and we can discuss them in our discussion periods. Okay, so just to conclude this module, I mentioned earlier that there's a number of different ARQ algorithms that can all be interpreted as kind of particular instances of the general sliding window protocol. And I'll give you 3 common ones, or I'm giving you 3 common ones on this slide. The first one is stop and wait ARQ. And stop and wait ARQ is arguably the simplest ARQ protocol, where we have a transmit window of 1 frame and a receive window of 0 frames. And so what does that mean? Well, basically it means that the transmitter can only ever have 1 outstanding transmitted frame before it needs to receive an acknowledgement. And the receiver is not allowed to buffer any out of order frames. So it can only accept frames that are in order. And basically, these two conditions together mean that every single frame needs to be acknowledged. And that's where the name stop and wait comes from. So the transmitter will send a frame, then it stops, it waits for an acknowledgement. When it receives the acknowledgement, it sends another frame, it stops and waits for an acknowledgement. And the next type of ARQ algorithm is the go back in ARQ algorithm. This is where the transmitter is allowed to have a number of frames outstanding, so it can transmit a number of frames before receiving an acknowledgement, but the receiver is still not allowed to buffer any out of order frames. And so we can send, let's say, frame 1, 2, 3, 4 in a row, and the receiver can then acknowledge receiving frame 4, and then we can send 5, 6, 7, 8, and go sort of transmit in chunks like that. But if we send frame 1, 2, 3, 4, and 2 doesn't arrive properly, the receiver will only acknowledge that it's received frame 1. It won't buffer any of the packets that were received after we had that gap, and we basically have to we have to go back to the first frame that was lost and retransmit all of them. That's why it's called go back in. And finally, the last ARQ type, selective repeat ARQ, is arguably one of the more general types of ARQ algorithm. This is where the transmit window size can be greater than 1, the receive window size can be greater than 0, so we can have a number of outstanding transmitted frames, we can buffer a number of out of order received packets, and it essentially corresponds to the example that we did earlier on in the module. As we're going to see, selective repeat ARQ is used in the TCP layer. So once we get a little bit further on in the lecture series and we climb up the protocol stack to the transport layer, we'll take a look at selective repeat ARQ again.